Hey, let's do problem 7.65. You can see it up here on the screen. Okay, we got a truck loading station that has a little and a post office, and we've got a small package up here. Okay, and you can see that it is going to have a package that's going to slide down this little ramp here, yepper, and then it's going to go here, and then it's going to, and after it does that, it's going to slide down here until it comes to rest. So it's going to go along this piece there. Okay, good. Okay, and they ask you a couple questions about it. They ask what's the coefficient of kinetic friction along that surface. They also ask you how much work is done as the package slides from A to B. So it's two different things that happen that we got to figure out, but they're not terrible. So if it goes from A to B, it starts at a high height, it ends at a low height. And they even tell us from A to B, well, that it starts at one and ends at another. So they want to know how fast it's going to end up going. Okay. So they ask us what's that coefficient of friction on the horizontal surface. Well, that's not terrible, okay, because we know that work is going to be done on this surface, and it's going to have kinetic energy to start with over here. It's going to have kinetic energy. Okay. And that kinetic energy is going to get smaller and smaller and smaller and smaller until it becomes none. Okay. So at this point, at point C, it's going to have no kinetic energy, okay, which is all right. Okay. Okay. And what happened to it, though? Well, it all got used up on that ground area. It became heat or sound as it slid across the surface. Whatever happened to it, it's somewhere else now. Okay. The surface did work on it. So basically, to do that part A, we have to use the work energy theorem. Okay. So in this case, the work became the change in kinetic energy. So what that means is that in this case, because the force is constant, we can say that work is going to be force times the distance that it slid. Okay. And that's going to be equal to the change in kinetic energy, which is going to be 1/2 the mass of the box times its final velocity squared minus 1/2 times the mass times the initial velocity squared. Again, this is the same kinetic energy equation. We're just changing it up. It's what it ends with. It's what it starts with. Okay. Now we got to put, what force was it that did it? The force of friction. Okay, so I'm going to actually put that on here. Okay, so that's the force of friction. And we have an equation for that, but it's got opposed, so it's going to be minus mu, the coefficient of friction, the kinetic friction, okay, times the normal force. Well, it's on a surface, a horizontal surface, so we can say it's mg, and that's going to equal the same equation that's over here, 1/2 mv squared minus 1/2 mv naught squared. Okay. Again, these are all doable, but you notice right away every term has a mass in it. So all of those, boom, boom, boom. We don't have to worry about those at all. Okay. And we know that the final velocity is 0. So it means this whole term actually goes completely away, which isn't terribly bad. Okay. So, and most of this information we already know. So let's rewrite this whole thing. So we've got negative mu sub k g d equals negative 1/2 v naught squared. Okay. So now we can move all this stuff over. You can see that that the two minuses are going to completely divide out. Okay, so we're going to take them away, and we can factor this and actually solve for what mu sub k is. And it turns out that it turns out pretty good. Okay, so we're going to have mu sub, whoops, sub k, I'm going to rewrite it here, k equals v naught squared over 2 g d, which is going to mean for us, we know that that velocity, when it gets to point D, they write it, or point B, they write it right up here. So it's going to be 4.8 meters per second, quantity squared, divided by 2 times 9.8 meters per second squared, times D, that 3 meters that it's been sliding down. Multiply all that out. Multiply it all out again, and you get a component of 0.39. Okay. I want to point out that your units cancel out awesomely. Meters squared, second squared, you have meters squared and second squared, so you are ready to go. Part B is the next part, and it asks how much work is done on the package by friction as it is shown in the circular arc from A to B. Well, we have a real problem here because, normally we would just say that, friction force equals mu times F of N. But whoa, F of N here, almost zero. F of N here, a little more. F of N here, a little more. Oh no, that's like a big problem, and it would be a real difficulty to try to solve that. So let's not. Okay. So what can we do about that? Well, we know we can go back to that work energy theorem, and hopefully we can find our way around it. Okay. Well, what kind of and so we know that there's energy at the bottom, and we know that there's also work done by gravity as it falls, and the work done by gravity as it falls is going to be the force times the distance. Again, the force of gravity is going to be constant because we're here close to the Earth. So it's going to be mgd. One question you might ask yourself right away is, well, why is it, mg is down and distance is down. So those are in the same direction. So we're going to call that positive work done. That's the work done by gravity. And you're thinking, well, it doesn't fall straight down, which is true. It doesn't fall straight down. But it does fall down as it goes. I mean, it has to go that whole distance. Gravity's going to pull it down that whole distance. It's just going to do it gradually as it slides down this little ramp. Okay. So the work done by gravity is going to be that. Okay. So we can figure that out. So we've got 0.2 kilograms, 9.8 meters per second squared. And then we've got the distance that it goes, 1.6 meters. We multiply all those out, and we get an answer of, come on, baby. Okay. We got 3.136 joules. That's the work done by gravity. Okay. So that's everything that gets done. But is that everything that makes it to that speed at the bottom? Well, the kinetic energy at the bottom, the change in the kinetic energy, is going to be that 1/2 mv squared minus 1/2 mv naught squared. And if we look at that, we know the speed at the bottom, 0.2 kilograms. We know that speed at the bottom, we used it last time, is 4.8 meters per second, quantity squared. And I'm not going to bother with this bottom thing, because I know it's going to be 1/2 times 0.2 kilograms. But no, this is 0, because the top, it says, starts from rest, the magic word here. So that guy's going to go away. Now, if I multiply all that out, 5 times 0.2 times 4.8 squared, I get an answer of 2.304 joules. So this is the stuff that gravity put in. And this is the stuff that we actually got out. That's what actually moved the box. So the amount that actually got used by friction is going to be the difference between those. So the work done by friction is just going to be the difference. 3.136 joules minus 2.304 joules. You just subtract those two. You get an answer of 0.832 joules. So that's all you have to do. You take those, you figure out the rest. It's not bad. And you can see that we got super lucky. We don't know integrating, no bad stuff like that. Just working with that change in kinetic energy and work, we can get an awful lot done.